Okay, uh, I was going to do this with a paper exam on the DocCam, but then I realized it wouldn't record. So I scanned the thing at the last minute before uh, coming here. So who's looked at the old exam? All right, good. Registered claiming too. All right, good. So I'm going to go through the answers and just talk about how you got there and give you guys a chance to basically ask questions. Okay, let me see if I can bring this up without showing you the answer. Sorry. Hold on, give me 1 second. Let me see if I can get this. Come on. Just bear with me. Okay, so let's start at the beginning. Question, the first CUDA question is meant to be sort of straightforward, right? So if you understood coalescing, understood how we get at memory accesses, you should be able to answer this one with some ease, okay? So the question says this: we basically set up this array A. I tell you what the size of each element in the array is. It's going to be 2 bytes. It's going to be a 16-bit float. Tell you what the warp size is here. I tell you the coalescing granularity. So like, I fuss with this a little bit from what the baseline GPU does, right? We changed the coalescing granularity a little bit. We're not worrying about caching at all. We're not worrying about any inter-warp type of access merging. And I'm just asking you to take a look at this one access to this one array that is using this thread IDX.X index, okay? And there's some math here that's basically multiplying thread IDX by whatever this I means. And then I give you this hypothetical thread block dimension, and then I ask you how many transactions, how many requests to the memory system will be generated by this thread block, okay? Who answered this question? Did anybody have an answer for it? Yeah.
I said 4 axes.
4 accesses, okay. Why 4?
Because I just did the code. I was 1, so it's going to be linear axis across threads. Okay, I've been loaded for what was the data?
Okay, so if I look at the axis across a warp, right, thread ID 0 is going to touch index 0. Thread ID 1 is going to touch index 1 because I'm just multiplying by I, right? So if I think about what happens across a warp, okay, now there's 32 threads in a warp. Each thread is accessing how much data? 2 bytes, right? 2 bytes, okay? So 32 threads, each accessing an adjacent 2 bytes And,
so then,
what is my total access for that one warp instruction? 64 bytes. What is the coalescing granularity in this setup? 64 bytes. So for one warp, how many transactions should I generate? One. Okay, so one warp here will generate one transaction. Now, this thread block doesn't have just one warp, right? I gave you a dimension 56, which breaks down into what? 8 warps. Which will mean that it'll generate how many memory accesses across this whole thread block? 8. Okay, it's 8. Thank you for being brave and answering the question. It's not immediately obvious. I'll show you the stats on how the students last year did on these questions. This one I think was okay. It was like 70% of students got this right or something. Yeah, go ahead.
Would you consider to be totally separate memory transactions, even though if there is a caching system or whatever, you still have the row buffer open on your DRAM or whatever, and it's still a hit and it comes in?
Yeah, that's a great question. So I'm eliding all the details of the memory system here. So when I say memory transactions at this level, I basically mean accesses to the L1 cache, to the very uppermost level of memory. Okay, so because we went into the depths of each individual layer of the system, you could interpret this in different ways. I really haven't given you enough information to answer anything more than that. And if you have those confusions during the exam, you can ask. And if there is ambiguity, if you feel there's an ambiguity in the question, state that on the side. And I do look at common wrong answers from what I wanted you to answer. And if there was ambiguity and you're right in your assumptions, then I'll give you the points. But what I wanted here was 8 transactions. Okay. Other questions? Yeah.
If the size had been like 32 bytes or something,
Yep.
for the coalescing granularity, would you then have just said 2 transactions? Half the thread got what they wanted, and then the next half would have to go.
So if the coalescing granularity had been 32 bytes as opposed to 64, what do you think the answer would be? 16. Because now every warp is going to want 2. Right? If I shrunk it further and further, I would just start spraying out. Okay. And I explicitly said here, assume there's no like inter-warp access merging, right? Like 'cause in a real system, if we're talking about like access to the L2, for example, they'll be merging in the MSHRs and the L1. I'm eliding all of that. I'm saying, look, just worry about what's happening in each warp, and then across this thread block, how many transactions am I going to generate? Okay. Other questions? So there's 2 parts to this question. Really, one is just understanding what happens across a warp, and then playing the jujitsu of like, these are the dimensions now. Like, this isn't no GPU. Well, some GPUs might, but like we had talked about coalescing granularities that were either 32 bytes or 128 bytes. We hadn't talked about 64. So you had to be able to basically extrapolate what we talked about to this problem. Okay, so the answer to this one, was 8. It's going to work nicely, or is this going to be, yeah. Maybe I'll do this. Okay, this one was 8. Okay, so now we change it. We change 2 things. We change the dimensionality of the thread blocks. So now it's not a linear thing. And we change I. So instead of I being 1, I is 2. So what do you think the answer is here? 16. Why 16?
Each block will be 2 rows, and because I is 2, 1 row will be 1 memory access, so 2 accesses per block and 8 such blocks.
Okay, that's a reasonable way to think about it. Any other answers? Yeah.
8.
Why 8?
Because, so 2 rows, would they share the same index?
Yeah.
So then they would actually,
So remember, there's no Y here, right? The Y dimension is in there, but it's actually not in the memory access. And so if I just look at this A access alone, and I think about what's happening across the warp, across all the threads, I basically have my X index. So I've written this out, in pen here, right? So the first 16 warps are going to have X index 0 through 16 and Y index 0. The next 16 threads within the warp are going to have X index 0 through 15 and Y index what? 1. But Y is not accounted for in this index arithmetic, which means that you will essentially get redundant memory accesses, right? Which means that the coalescing system, being smart, will just collapse them into one. And then how many warps do I have here? I have 8. I actually have the same number of warps. So what is the total number of memory transactions I'll need for this whole thread block to access A? Any takers? No. Okay, people are confused. Zach, you had it right. It's 8, right? It's 8. And I think you got it right once you realized that, you know, once the index was wrong. So it's actually the same answer as the previous question. Okay, every warp generates just one transaction because there's just redundancy that's going to get broadcast and coalesced across the warp. And so the answer here is also 8. Okay. Questions? Yep.
Can this broadcasting be happening across warps or only this one?
So in this particular, so in general, it's only across one warp. Like this coalescing mechanism happens on individual warp instruction basis. Looking at access is to my L1 cache. The highest level of the memory system, the first place I go after the load store unit. It's only looking at accesses within one warp. Now, the cache or some kind of merging system may take accesses between warps and also merge them together so they don't redundantly access the next level of memory. But in this question, that's been elided because we've said ignore interwarp merging. Okay, good question. Other question. If I had made I 0, what would the answer have been? 8. Now they're all actually accessing the same thing, right? Because they're all accessing A0, but since 8 warps and there's no interwarp merging, you're still going to end up with 8 transactions in the memory system. Okay, so because of the way this thing was sized, you know, you couldn't make it any better than 8, essentially. Other questions here? So one thing that, you know, that the student brought up is that if the question doesn't give you, you know, details about row buffers or details about caching system, or like, don't go off into the weeds on details that are elided by the question, okay? Because you can make this way more complicated, right, than it's meant to be. And so you should, you know, the question should be guiding you to what's actually important in the question. Right. And, you know, if you read the question carefully, there is no other way to interpret this other than the way these answers, yes.
Do that 0 through 15 and 0 through 15 will be scheduled together in one block.
Yeah. So that is the way that multidimensional thread blocks will get scheduled. We covered that, I think, at some point way back when we looked at 2D thread blocks. But yes, you do have to do some time. Good question. Anything else so far? So these are so far the easy ones. They weren't as easy as I hoped they would have been, like in the exam when we gave this. So then we get a little bit bigger. So now I'm going I equals 8. So now how many memory transactions am I going to generate? 64Y. All right, so you're going to get 2 per warp. Because now I have this stride, right? So essentially, I'm going to have every thread's going to be accessing 8 2-byte elements separate from each other, right? And so if I smash that down into how many each warp is going to generate, you're going to end up with 4, right? Wait. Yeah, you're going to end up with 8. You're going to end up with 8. You're going to end up with 8 accesses in each warp, right? And again, that's because I know it's 2 bytes and I know they're separated by 8 by 2 elements, right? 16, and I know there's 64 size coalescent block. So I can figure out for each warp, how many transactions am I going to need? It's going to be 8. I know I have 8 warps. 8 by 8 is going to end up being 64. Okay, and that's the answer here. Okay, questions on this? You can expect something like this that's going to test your knowledge of like what's happening with coalescing and memory accesses. This is pretty basic good stuff. Okay. Let me go to the next question. Let me see if I can make this not jump around. Let's see, that's two, so. Here's question two. All right, my stupid scan doesn't work. Okay, so I'm gonna do this. Just quickly pull up the paper on Piazza. So this is the raw file. All right. Oh, that wasn't actually the first question either. Because my scan screwed up. All right, so this was actually the first question. That was the second part of the first question. So this was asking about the Cindy efficiency, okay? And again, I've given you a theoretical warp size 64. I give you a size, a dimension of the thread block that you're going to spawn. I give you a little piece of code, and I ask you what the Cindy efficiency is of a particular line in this code. Okay, what's the answer here? What percent? 50%. Why 50%?
Because the modular will wrap around.
What's that?
The modular will wrap around.
The module is going to wrap around to 0. So basically, I take a look at, okay, what is the condition that's guarding this particular line of code? And how does it behave across a warp? Okay, so this particular line of code is doing this mod 32 thing. So that means every warp is going to have, 0 through 31 as the result of this modulo, regardless of how many warps I've spawned. And then it's testing it against less than 16, which means that in every warp, wait a minute as well. So yeah, your warp size is 64, right?
Two elements.
So 2 elements, yeah. So basically, you're going to have 0 through 15. And then 32 to 46, so it's not, what's that? 40. Wait a minute, what am I doing here? So your thread IDX is gonna go up to 256 across the warp, there's gonna be 64 within each warp. Oh yeah, I'm sorry. Yeah, you're modulating 32, and then you're testing less than 16, right? So you still end up with half of them all, right? So you basically have to do the jujitsu of like, how are my thread IDs spread out across my warp? And in this one, it's just straightforward linear. You have to figure out, well, if I mod 32, what is that going to do to these thread IDs? So it's going to be 0 through 16. And so these ones are going to go in. The first 16 are going to go in. The next 16 are not going to go in. Then the next 16 are going to go in. And then the next 16 after that are not going to go in. Right, so even though the warp size is 64, I get this weird pattern of like the first quarter go into here, the next quarter do not, the next quarter do, and then the next quarter do not. So you have to sort of do this arithmetic either on paper or in your head to figure that out, and then you just look at, well, what is the average across the warp? Well, half of them will go in here. So the Cindy efficiency is going to be 50%. Okay, make sense? All right. So then this one was asking, if I change up the warp size, what warp size here will give me 100% Cindy efficiency when line 7 is executed? Okay, what's that? 248. Was it 16 as well? Did we do 16? Yeah, 16 too. Basically everything that's less than 16, right? And if you go over them, you start basically, that condition, right? That less than 16 business, is it going to affect, what's that?
Including 32.
No, 32 would not.
32.
So if I do this, if I mod 32, so I will get 0 through 15, and then I will get 16 through 31. 16 through 31 is going to be greater than 16. So it's not going to be 100% efficient. But like, if I think about, if I have a warp that's 32 wide, you got it? Yeah. Thread 16, yeah. 17, like, their question was, what is gonna be 100%? Right, so the smaller you make the warp size, obviously, the like easier this is for the GPU efficiency wise. Yeah, question.
The thread block size is still 256 though. So you wouldn't-
Right, okay, so. So if you assume that it's 256, so you're thinking about things that are falling off the end, right? That's actually trickier than I intended this to be. So that would mean like, so if it was 2 threads per warp, it's even. If it was 4 threads per warp, it's still divisible by 4, right?
I see. So you would still have thread ID 0 through 255 regardless of the warp size. Right?
But it doesn't matter because I'm modding them by 32. Right? Does that make sense?
You think thread IDX would be 0 to 55, it would just be 0 to 1 minus that like warp size, right? Like 0, 1 to 3.
The thread ID.
Thread IDX at X would be like maximum of 3 if you have 4 threads in a 1.
Right. Correct. And so I think where you're getting confused is that all the warps don't go in here. It's just that all the warps all the threads in the warp either all go into the if or they all go into the else. Right? So it's still 100% efficiency because there's no warps that are going in there that are partially active. Does that make sense? So I see where you're coming from. If it had been some weird multiple that was not a power of 2, this would have actually been trickier because then you would have had to worry about the one on the end being diverged and going in there potentially, but that wasn't the case here.
So the thread IDs will be based on thread block size or warp size?
What do you think?
It will be based on thread block.
Correct. Correct. The thread IDs are based on warp size. Or sorry, thread block size. You really don't, so there is sorry. They didn't even give you access to the warp size in early versions of CUDA. It was only the thread block. It's only recently that you could even like read what the thread block size is. So it is thread block that determines the program. Okay. Zach, you looking for your question? Other questions? These, they ended up being a little trickier than I, had originally intended, but I can't make them super easy because it's a 600 level class. All right, questions on this. So that's all the question 1. So question 1 was meant to be like the sort of basic, do you understand what's going on with CUDA and thread blocks questions? Okay. And generally, I think it was pretty well done. Let me show you the stats here. People like to see like what happened. I think it was like 70 some. Give me a second. Just gotta make sure I don't deep blind anyone who took the class last year. Statistics. Okay, here we go. So yeah, question. So the first one was like 88% average, right? That's the 50% question. And then the other one was 83. So yeah, people actually did pretty good here, right? It was actually, fairly high average. 1.4 was less good. 1.5. So 1.4 was, when was that? That was the number of transactions one. So people screwed up the 2D transaction one. That's what the 60% was. And then this was the 64 transaction one. So, people still did fairly okay. It's actually better than I remember it being. Okay. So let's go back to the exam. All right, any questions on 1 before I move on? All right. Question 2 is harder, okay, by design. So now I'll give you some real CUDA. This is a real CUDA program that's doing a real thing. I actually took the example from the textbook, the One Way Who textbook that covers CUDA. That's some of the courses that it's based on. And it basically shows you the code for compressed sparse row kernel, where I have a sparse matrix that's being multiplied by a dense vector, okay? And I'm not just doing like a dumb dense multiplication algorithm, I'm actually doing a sparse algorithm, which means I've encoded the data in a sparse way for the sparse matrix, and I'm accessing that data in, in its sparse representation in the code itself. And so there's a pictorial example here of logically what's happening, where each of these squiggly lines is one thread. So basically each thread, and the whole thing is an example where we're just going to use 4 threads just to make things simpler. Each thread is sort of processing each of the rows of the sparse matrix, multiplying the value by the dense vector, which is the gray thing, and then storing the result out in a dense vector, which is the output. Okay, that's essentially what's happening here. And the format is this thing called compressed sparse row, which if you don't know what that is, you don't really have to know that to answer this question. You really just have to look at the code. But it basically is a way to encode a sparse matrix without storing all the zeros by keeping a bunch of pointers around, right? And so we've got like a bunch of row pointers that point to where each of the individual rows begin in memory. And then we have we'll basically then have a bunch of column indices to say, well, where is the data, okay, associated with this, but like where in the matrix is this thing supposed to be, this particular value, and then we'll have a value array that has each of the values for the sparse matrix. And so it's color coded. So basically it's like, well, the first row of the sparse matrix is encoded by all the blue stuff, the second row is encoded by the green stuff, and the third row by the yellow, and then fourth by the red, okay? And then you can look at this code, which is processing these data structures. It's not all that much CUDA code, but it's, sort of complicated if you're not used to reading it. And you sort of have to parse what's happening, okay? You need to figure out like what's going on with this row index, and then how is that row index being used to access these various data structures, and then what's going on in the inner part of the loop, okay? And you probably just read all this and you don't really like internalize it until you get to, because it's like, all right, fine, whatever, what's the question? And I generally, you should approach it that way. Like, don't sit there reading the code forever, figure out what I'm asking you first. So the first question asks, if I assume a 4-thread warp and a small sparse matrix, so I'm going to use this exact sparse matrix in the example, because this is a data-dependent application. Depending on how sparse and the configuration of your sparsity, there will be different characteristics on how it behaves in hardware. This is the kind of stuff that's really hard for GPUs, right? Like dense matrix multiply is fantastic, because everything, the shapes. Here, it's like, I don't know how sparse it is until I start processing it, and then bad stuff can happen. So if I'm doing this, and I'm assuming a 4-thread warp, and I'm going to use this exact example that I've got above, how many iterations does the warp make through the loop? Okay, so I'm assuming that I can process this all with just one 4-wide warp, and the question is, how many times do I go through that loop? What is the answer? Anybody solved it? Yeah.
I said 8.
8 times, okay.
But that was one thing I wasn't sure about.
Okay. Why did you say 8?
Because the maximum content has to go through is 8, and so all the threads work in parallel, and at most we'll have to go through that loop 8 times.
So you're getting 8 from basically the width of the call index and the value array,
Yeah.
right? So that's essentially how much work has to happen, which is fair. But remember, this is happening in parallel. I'm actually bolting 4 things together here. Okay. So on the very first iteration of the loop, what is happening on the very first iteration of the loop? How many threads in this 4 warp thing are going to be active? 4. Why? Well, all 4 of the rows, if you parse what this code is doing, all 4 of the rows have at least one non-sparse value. So I am essentially going through and I'm grabbing the very first element of each of these 4 rows, and I'm processing it in that first loop iteration. So I get 4 data elements done in that first one. And I knock them out. Question?
So is the answer 3 then?
Yes, the answer is 3. Okay, so the answer is actually just the length of the longest sparse row. Because every iteration of the loop, I can only eat one element from any of the sparse rows. And so the number of loop iterations is bounded by however many non-sparse elements I have in that row. Okay, and you parse this code, or you just even, look at, I would, some students I think got this by just like looking at the example, right, just the picture, right, to sort of understand the processing. Or you can try and parse the, the code. This is a little bit more explicit on what's happening here. Okay, but the answer for number of loop iterations is 3. And your answer is wrong because you sort of didn't account for the fact that multiple things are happening in each cycle.
Yeah, well, I used it in what I did made more sense when I put the second part, because I just do the numbers, subtract them all.
Right.
Which threads are active.
Right, exactly. So then that should have tipped you off that maybe this one was busted, right? So, okay. Any questions on this? Let's see, if you read the code, you basically have to be looking at, if you read the code, like there's a loop, right? And each of the threads are doing the loop, but each of them has a different starting point and each of them has a different loop bound because they're reading these things from memory. And so you have to actually look at the data structure to figure out, well, like which one is going to go the furthest based on where it starts and where it begins. Okay, and if I looked at the numbers here, what two numbers, how do I figure out without that picture? If I didn't have the picture on the left, without the logical view picture, how would I figure out the longest one is? Yeah.
The biggest adjacent difference.
Exactly. So I take a look at the row pointers and I look at the biggest adjacent difference because that's what's encoding the sort of run length of each individual sparse row. Okay. Now, we didn't study like sparse rows and sparse row compression in class, right? This is just an example of like a CUDA program that I'm asking you to internalize on the exam. Okay, you'll have something similar. Like I've done reductions in the past, like I'll give you enough to be able to understand it, and the code will be there and the code will be correct. But that's kind of the hard part here is trying to tie these things together. Now, if you know this algorithm and you've written the CUDA code before, then this is like straightforward for you. But if you haven't, which is most of the students, then this takes some internalizing to try to figure out what's going on. So the number of loop iterations here is 3. Questions on that? All right. That one, let's see, let's do this in one. So that one was 2.1. So most people got this, 75% average on that question. Okay. Okay. So then the next question, I think, falls on this, right? Like, all right, fine. So that's how many times it goes through the loop, but like, what is my average efficiency? Like how frequently, is the thing active? Okay. Does anyone have an answer for this? Yep. 67, do you have an answer? 50, any other answers? What's that? You have 67? Okay, 67 is right. Okay, so how do we get there? Who had 60? You had 67, right? Yeah, go ahead.
Each row executes, so in each iteration, there will be one element from each row executing.
Mm-hmm.
So the first iteration has an efficiency of 100, the second one is an efficiency of 75.
Yeah.
Then it's 25, but then we are done, so there is no more iteration.
Exactly. So basically, it's like you take a look at each iteration, what's happening. So 100 on the first, so that's 4 on 4. Then the next iteration, you've got 3, so that's 3 on 4. And then the next iteration, you finished every row except the green one, so then it's 1 on 4. So then you add the numerators, add the denominators, it ends up being 2/3. Okay. Or you could actually just, if you understood the problem well enough, it's just the density of this matrix, right? Like, well, is it actually? No, it's not. It's not because of the distribution. Yeah. So you can't just do that. Actually, that was a common mistake. Some people just did the density of the matrix without considering the distribution. Because if you think about it, right, like the matrix is distributed differently than you'd have 100% technically. I could have had 100% here if I had just had 2 in each row, even though it would just be 50% sparse, right? So it's not just the density of the matrix; it's the distribution of that density across the rows. Or if you don't care about the problem and you just literally you could read the code, right, and not understand anything that's happening, and you could compute what it would be. I personally like looking at the pictures, right, and conceptualizing the problem. But if understanding the code is much simpler to you, you could parse through it and try and sort of figure it out from that as well. Okay. Questions? And that one, let's see, that one people also did pretty well. Set right on the average of the exam, pretty much 70% mean on that question. Okay. So then it asks, assume a forward thread. No, wait, that's the question we just answered. B. So then came C. So C is asking that I scale this up. So my toy example goes away and I give you some arbitrarily large sparse matrix. Okay, so it's gonna have more than 1,000 non-sparse entries per row and thousands of rows. Okay, so a much bigger matrix. And I'm gonna launch these thread blocks that have just this X dimension, so I'm not doing any 2D craziness, it's just, thread blocks of a certain size. I'm gonna tell you that there's a 32 wide warp, I give you the coalescing granularity, and all I'm asking you to do is identify all the reads and writes that, given this configuration, and given the sort of ambiguity in the rest of this question, generate more than one memory transaction per warp. Assume that everything's that all the floats are 4 bytes, and then everything starts out being a line. Okay, so any takers on what the right answer is here? So which one of these essentially might not be coalesced? And there's a multiple select, so it could be more than one.
Second and third.
Second and third, so this one and this one. Okay, so if we go back to the code, so I asked you about this one. Okay, that's one of them, which you're saying is coalesced. How do you know that?
Is, if you take a look at the row pointers, I
Yep.
think at that point they are not, like they're still, the access is still continuous.
Exactly. Take a look at the indices. The index on this axis, the row pointer, it's indexed by the value row. If I look at how I compute row, it's got this kind of magic plus thread IDX thing that I said was great for coalescing. And if you work out the math on this, or you just, took back the envelope, was like, okay, Roger said this is fine, it should be fine. Now, it could be trickier. It's like, oh no, with this sizing, it's not fine. But for this case, it was fine. That means that that's just going to generate one access, right? It's going to generate one nice big 128 byte access that services everything. Okay, so that access is fine. I know I'm not going to have multiple. So then I go look at the next one. Okay, so this is the CSR matrix call ID X. So I look at this guy, and I see that there's I in here, right? And normally when we see a loop and there's I, it's usually good to go, right? Because it's like all of the threads are doing the same, like I equals 0 all the way to the same bound. But in this case, is that happening? In threads across a warp, are they all going to have the same value for I? What do you think? No, right? I mean, look at how I is initialized. I is initialized with a data value. You're reading some value from that row matrix, which means that I'm going to get a different value potentially. And I've got this giant matrix, right? Remember, this question says, could this be a diverged access? So that I is not going to behave nicely. That I is going to be all over the place based on my warp. So when I get to this access, it's indexing that call IDX by that I value. I can't say for sure that it's coalesced. In fact, it's more than likely not coalesced. Okay, so the second one could generate more than one memory transaction. Follow me so far? The third one is X call. This one is the easiest one, right? Because this is like a data dependent thing, right? I'm reading something from this column IDX. And again, like, I don't know what this is. It's a data dependent value. And then I'm indexing by that data value. So it's going to be all over the place depending on the dimensionality of the matrix. So that one also is going to have more than one transaction potentially. And then finally, I've got my right to Y down here. And again, it's essentially the same thing that was happening up here with the read from this array, because it's using the row index and everything's nice and coalesced on the right. So that one's not a problem. So the correct answer here was, as was stated, that it's these two that are the problem that would generate more than one transaction. Okay. Questions? That one, 2.3, that one was less well done. That one was 50%. I think a lot of students got exit call, but then they missed the call ID exit I. They're used to just I being fine in typical programs and trace through where I came from. Yeah.
So, for that type of question,
Yep.
would you get partial credit for?
Yeah, I'm pretty generous about partials on these kind of like multiple choice things. I try to give credit for common wrong answers, not all credit, but some of them. Right. Anything that shows thought. I'm trying to judge thought here. Did you understand what happened in this class? Other questions? Okay, so that's it for CUDA. Easy, hard, makes sense? Nobody's willing to say. Do you think you can do as well as the last class did on similar challenging problems? Remember, you do get your note sheet. Everyone brought in a note sheet last time. You know, so it can be useful just to sort of give you a comfort blanket at least. And you're still a week out from the exam, so maybe you don't think you can get 70 on this now, but like, got 7 days, so. All right, so then we go into the hardware one. This one, the first part was this sort of very detailed example of what's going on in the operand collector. And it's similar to the example I went through in class, except I changed a bunch of stuff, right? Like the number of ports are different and the sort of way that it operates. I give you a very precise schedule, and you sort of have to trace through logically how this is working based on, you know, the configuration of the operand collector. Unfortunately, I don't have the answer written out. Who solved this fully? Some folks. Okay, some folks. Let me see. What do I have? I have 30 minutes. I will give you the answer to this. It just takes a long time to step through. Okay, let me see what I've got. So I've got this. This one's actually pretty quick to go through. So I'll go through this before I do it. And then this one was an absolute disaster last year. I don't know why. These ones are actually pretty quick. So let me go through the quick ones first, and then I'll come back to the operand collector. I'll walk through as much of it as I can, and I'll give you the answer if I don't make it all the way through, okay? So skip operand collector, and we go to SIMT stack. So this is trying to, you know, so the CUDA stuff is saying, like, do you understand how CUDA works? And then this is saying, understand how the SIMT hardware that's implementing this sort of, you know, CUDA representation works. And so I give you this piece of code. Again, this is a toy piece of code again, where, you know, there's basically some, you know, input dependency here, and I made some things by thread IDs, and you're going to end up with some kind of control flow divergence, and you sort of need to understand what's happening with the stack, okay? There was a little bit of ambiguity in this question, which I'll talk about in a second, but I just want to see what people did. And so the first question basically asked, the first time line 6 executes, what entry is on the top of the SIMT stack? Okay, so remember, the top of the SIMT stack is like what I'm doing right now, right? Because you sort of build up this stack, right? And so at the very beginning, there's like one entry on the stack. As things start to diverge, you start pushing more and more entries on. And then as things start to reconverge, you pop them back off. And so what this is asking for is just what's on top of the stack right now. So RPC stands for reconvergence PC. I don't know. I didn't actually say it in the question. Maybe I should have. Hopefully most people understood what that meant when they came in to write the exam. So RPC is the reconvergence PC. So what is the reconvergence PC for an instruction executing at line 6? 8. Why is it 8? That's the post dominator of the most recent control flow, right? The most recent control flow is that while statement. Okay, so that's a branch. It's a conditional branch that's being executed. It's actually executed at the bottom of that, but it's irrelevant to this particular question. But you know, you're basically going to have a reconvergence PCB. Well, I guess it's not irrelevant. This probably should have been do well. But just looking at this from the C perspective, you know, the reconvergence PC at this point should be 8, right? Because that's where they're going to come back together. Okay. Now the PC, you know, what would the answer be here? 6, right? 6. Or if you consider it the next PC, because this is the issue point, then it could be 7. I gave points to both answers. It was sort of ambiguous as to which one it should be. Like, this is just where the thing is right now. I just wanted you to know that the top of the stack was what you were doing right now. And then what is the mask? 0110, how did I figure that out? From the input, right? So I have to read the code, right? I can't just like, I have to figure out like, okay, who actually went in here? So I take a look at the first if condition, I'm indexing the input by my thread ID. I'm checking to see if it's less than 16, so then I have to look at this input array, which elements in this input array are actually less than 16, also two middle ones, two outer ones are not. So I'm actually not gonna execute, the two outsides, so I do need the two insides. And then I'm going into to the while loop. Well, no, actually, I was right. The while loop is going to test the condition up at the front. And then I check to see if I is less than whatever this bounds is. And, the bounds is basically whatever was in that input array again. And the first time through I is 0. So all of them are going to, everyone who came into that first if is going to go into the while the first time. So that means those two inner ones are going to be active. So it's 0, 1, 1, 0. So you had to trace through the code to try to figure out what happened across the board. Trickier part of this question was, what is the total number of entries on the SIMT stack at this point? What do you think the answer might be? I was actually very generous with this because there is some ambiguity in how this might manifest itself. But what do you think? What are some potential answers? What did you get? Who solved this question? Yeah, go. 4. Okay, that was the answer I wanted. It's 4. So where do I get 4? So in the beginning, there's 1. Okay, so it's very top, like those pieces of code before I get to any control flow, there's 1. And then I encounter that if statement, right? And then what happens when I get to the if statement? How many entries do I push onto the stack at that if? 2? Because I actually have 2 ways that I can go, right? And I need to record the other one because it's going to have to come back and be done at some point. So when I get to that first if condition, I'm pushing 2 entries onto the stack. So now I have 3 entries on my stack. And the top one is going to be the one that goes through the if. Okay. I think there's something in the question that states you have to do the ifs first, just to make it clear you're not doing the else first. Okay. To disambiguate that case. Because in theory, both are equally valid, right? But you have to make an assumption so everyone gets the same answer. So it ends up there's 3. And then I get to this while statement. And inside the while statement, it's sort of like I'm assuming, so there were 2 ways you could have done this, right? One is assume that you just modified the top of the stack for the while because everyone actually goes in, so there wasn't 2 entries. The other assumption is that you popped the new entry on for the while and then sort of executed the while until it was done and popped it off. And that was the 4. I also give credit to 3 because maybe it didn't do that. Maybe it just updated the top of the stack directly. We didn't talk about how that works inside while loop. So either was a valid answer. Okay. The point of it is to know that, it had to be at least a depth 3 because you were inside these 2 conditionals. Okay. Questions on that? All right. Then the other one is this, the last time this thing executes. So the last time it executes, RPC and PC are the same, right? There's no difference. The difference is the mask. And what is the mask value on the last time it executes? 0010, right? It's just whatever. You had to take a look and see like, okay, well, this one is going to finish first, and then this one's still got a bunch left, so it's going to be the last laggard thread that's running, okay? And entries on the SIMT stack is the same. Whatever you assume in the first one, it should be the same in the second one. Yeah.
Wouldn't it be 0, 1, 0, 0? Because the 81 has to occur more times to get the 16.
So there's a 15, right? So I starts at 0, it goes from 0 through 7, and this one is still active. As soon as it gets to 8, then it's just this one that's left over. Make sense? Okay. Very last one is line 10. So you're basically going now to the other side of that conditional that was pushed onto the stack. So what's the RPC the first time line 10 executes? Here's the code. This is line 10. What should the RPC be? 11, right? That's the convergence point of that if else. You could draw the control flow for this if you wanted to, or you could just eyeball it if you're sort of familiar enough with it. But 11 is where it should come back. PC is, yeah, whatever. It's either 10 or 11, depending on whether you consider PC or next PC. And then the mask here is what? 1001, right? The other threads, the other ones that are going the other way. And then the stack depth will be what? 2, right? Because you've done all the madness you did with the loop is gone, right? You exhausted that whole path. Now you just got these 2 entries, of which the top is the else bands, and then the bottom, there's only 2 entries, and the bottom is when you get back to like everything, everyone back together again. So there's 2 entries. Okay. Questions on this? Yeah,
I just wanted to confirm the answers to 2 are the same as 1 then.
the answers to 2. No, so the mask is different.
Oh.
Yeah, the mask is different by a bit. Question? You got a question? No. Okay, how do people do? Let's see. I think this one was okay. This is question 3, right? Yeah, so 70-some% on these 2. Or no, wait, that's this one, 71%. Reasonably well done. This was the worst done question. I don't know why. I think people just didn't think I was gonna ask it, so they didn't study it or didn't write it down. I don't know. So how do you solve it? So it's talking about physical address mappings, or maybe the damn thing was too long and they just ran out of time at the end and then people wrote down random stuff. Maybe that was the issue. Okay, so what was this asking? So it says you're given a 16-channel memory system and each channel has 16 banks. And there's a 64-byte transaction size bus, okay? So that means every time I go to memory, I get 64 bytes back from conceptually one of these banks. And I'm asking you to construct a physical memory mapping that places adjacent 256-byte segments in adjacent channels. So structured channels on 256-byte segments, while maximizing row buffer locality and bank level parallelism. Okay, so you have to parse those words and understand what I mean by where I want those placed. Assume your workload has typical bit entropy. What do I mean by typical bit entropy? What would that mean? In the
Lower bits change frequently.
Yep.
And the upper bits are stable.
Right, so the lower bits are much more frequently changing, the upper bits are much more stable. Okay. Now, okay, so that's typical bit entropy. These 2 phrases, maximizing row buffer locality. Given the bit entropy, where do you think the row buffer bits should live based on typical bit entropy if I want to maximize row buffer locality? Yeah.
Column should be lower.
Columns should be lower, right? I want rows to be more because I want more things more likely to land on the same row because the bottom bits are changing more. Now, in converse, I asked you to increase bank level parallelism, which where would I put it in the address space if I wanted to maximize bank level parallelism? Up or down? If I want to maximize parallelism of a thing, I go down, right? Like the bit entropy stuff is moving fast down here. So if it's moving fast, I want a bunch of them to be lit up concurrently. So if I want something to maximize parallelism, I shove it down. And if I want something to maximize locality, I move it up. Okay, because these bits are more stable and these bits are more frequently moving. I think that a lot of students missed that point when they answered this question, or they didn't quite understand what that meant. But that's sort of, because there's not enough information to really do this, And then there's one other thing that I'm requiring you to do, which is make sure that the channels are on 256 bytes. Okay, so that means I need to somehow, make sure that there's this 256 offset for my channels. Okay. So I'll give you an example of what I want, right? Like, so that I'm talking about the lowest bits in the bus and the uppermost bits in the bus. And there's this little table here that basically says like how you lay them out. And then you need to tell me how many bits, right, are in each one. And I give you this little example, like partially because I wanted to auto grade this, right? And I couldn't, like, if I asked you to draw that thing, it was hard to auto grade. And if I asked you to do a table, it was easy to auto grade. So, so we did it as a table. Yeah, hopefully that's pretty straightforward. So fine. So let's talk about the real answer. Did anyone actually answer this? Okay, just one, both of you, okay? Sort of? All right. All right, so let's start at the bottom. What should be at the bottom? Byte and bytes, you can't get around that, right? Like every time I go, I'm gonna get this amount of bytes. Like how many bits are in the byte in bus field? 6. Because I know that's 64 byte transaction. Every time I go to memory, I'm getting 64 bytes back. Okay, I can't index within that. So that means that's sort of locked in. All right. Now, what should I do next? Banks. Okay, why banks? Increased parallelism, right? These are the high entropy bits. I need to put banks in here. Now, do I put all the bank bits in there? How many bits do I need for banks? 4. Okay. Do I put all 4 bank bits next? Yeah. No. Why not? So there's an additional constraint. What other constraint did I have in here?
Row buffer.
No. Somebody raise a hand. Yeah.
Adjacent channels.
The adjacent channels. If I put 4 bits, okay, so if I have 6 bits in the bus, and then I have 4 bits for my banks, I've got 10 bits, which means that anything I put above that is going to be offset by at least what? 1K, right? Because I've got 10 bits down here. So what do I need to do to adhere to that 256 byte segment? 2 bits. So I have to have 2 bits of my bank. So I have 6. Let me see if do I have the answer? Oh yeah, I have the answer. Was I showing you guys the answers? Yeah. Oh, I didn't freaking scan them. Yeah, that's fine. Here, I'll show it to the people on the screen. And then I'll, right. It's easier if it's written up here, so that way you guys can see it built, but all right, you're gonna have to keep this in your head, just because I can't draw on this right now. So the bottom is gonna be bytes in bus 6, then I'm gonna have banks 2, okay, low banks 2 bits, and then what's next? After the banks, after the low part of the banks. Channels, how many bits? 4, because there's 16, okay. Then what am I gonna do? Upper banks, how many bits? 2, okay. And then what? Column, right? Because now what's left is just row and column. And I know that I want to maximize row buffer localities, I'm gonna stick those last. So I got the column. Now, how many bits for column? This part was kind of challenging. Squares. So it's a square. So I know my column bits and my row bits are gonna be equal. So then the question is, well, how many total bits did I need? Right? So who has an answer for how many bits they need for the column?
10.
What's that? 10. Close.
If you want to draw.
I don't know if that's helpful. I might wanna. Okay, how'd you get 10? How'd you get 10?
I got a 36 overall.
Okay, yep. 36 overall. How'd you get 36 overall? I told you how big the memory space was, right? The size of the memory space is going to be the total number of bits you need for the physical address. And I told you it was, I told you that it was 64 gigabytes, which is going to be 36 bits. Okay. This is undergrad stuff, right? You guys should be able to like translate that. You have a calculator too, but please, please don't be there dividing by 2 like 36 times. Gig is 10, gig is 30, right? All right. Right. So 36 total. So then how do you get down? What do I do next, Zach? What do I do next?
You subtract everything.
You subtract
it all.
You subtract everything you used, okay?
4 bank, 4 chains. But
Yep,
so you got 22.
correct. So I know the total is 36. I already used up 6 plus 2 plus 4 plus 2, because that's what I strided already. So I have 22 left. And I told you it was square, which means that they need to be equal among the banks, the rows and the columns. So that means there's 11. So I get 11 for column, and then the very last thing, all that's left is row, and then I throw the remaining 11 bits there. Okay. Nobody got this completely right. I look back, there are 0 people who got all 12 points on this question. I don't know why. I actually don't know why. Maybe you were close, I guess, with your answers. You screwed up. That probably would have been 11 out of 12. Or maybe I just would have given you 12. You were the only one that was that close. All right, questions on this? I don't know if I'm going to give you a physical mapping question, maybe not this involved or this much points, like, but you still should understand this. You could expect some kind of question on this. Make sense? All right. I have 15 minutes, so let me go back to, really, I need to draw this or else it's just going to be a huge nightmare. Let me see if I can very quickly get this up on my iPad. Because I also want to share this, you know, so if I do it on the board, right, then it doesn't translate. What am I doing? Give me 1 sec. Let me see if I can just bring this stupid thing into the presentation and then mark it up. While I'm doing this, any questions? I can think and type at the same time. General questions about the exam? Yeah.
For that last question.
Mhm.
We did the banks before the columns. Is that because banks are shared in the same?
We did the banks before the columns because I asked you to maximize parallelism among banks.
So it takes precedence over the.
Yeah. Well, and the row bits were up, right? You had to make sure the column was next. All right. Keynotes. My apologies for this not being ready.
Is there anything else you can ask us to maximize about?
I can ask you anything that's in the slide. Right, so there's no guarantee, you are not gonna get the exact same set of questions, right? You know, there will be some inspiration from some of these questions, but I can't ask you the same thing, I mean, you know. But it's a flavor and the style of questions will be similar, just it may be on different mechanisms. Okay. Let me see if I.
Is there another hardware structure that we might be expected to know that's really important within the SIMD pipeline other than the operand collector?
So you should understand what's happening with schedulers. You should understand what's happening with scoreboarding mechanisms. We talked about those. You should understand the SIMT stack is sort of them, right? You had a question on that on this exam. I usually do something on SIMT because that's kind of fundamental. Yeah, if you take a look at that diagram that we went through, like any of the elements in that diagram are sort of fair game. Many of them are very similar to what's in the CPU, right? Like there's I caches, there's data caches, there's different memory flavors. The sort of unique ones are the SIMT stack, the high register file, and the various scheduling mechanisms. So any of those are sort of uniquely different from stuff that you might find in the CPU that I could potentially ask a question on in some level of detail. Does that answer your question?
Yep.
Okay. There we go. All right, so we'll bring this up and then I'll bring up this thing. I think that, folks on Zoom, is it still being shared with you? Is anybody there listening? Is there anybody out there? I know people log in. I don't know. Okay, stop sharing. Let me share. So just there, so like it looks like you're there. I don't actually check, so it's not getting you anything if you're not listening. Okay. Now it's visible. I didn't push this button. Okay. All right, so two people solved this, so they can sort of walk through this with me. And see if you got the same answer that I did. And explain to you why it's right or not right. I still have almost 10 minutes. All right. Somebody who answered this, tell me what happens on cycle 2. I gave you cycle 1. Okay. What happens on cycle 2? Zach, go ahead. I'm volunteering you.
Bank 0, work 1 R7.
Okay.
Bank 1, you can do work 2 R2. And bank 3, you can do work 2 R5. Oh.
Correct so far. Okay, how did we get here? So cycle 1, so cycle 0, this thing goes into, like, I basically allocate the collector unit, right? That's what's happening on the top. In cycle 0, the collector unit is allocated for the MAD instruction. I'm telling you these little subscripts telling what bank each register is using. And so basically now I have these 3 adds or these 3 reads that are pending for this MAD instruction. And there's a bank conflict here within the MAD instruction itself because 2, 7, and 1 actually want bank 0. So in the very first cycle I gave you, all right, fine. So warp 1, right? That's the warp that this instruction is associated with. We're going to read from register 1 on bank 0, and then we're going to read from register 3 on bank 3. Okay. And then Zach just gave us the second cycle where I take a look at what's happening now. So in cycle 1, I was plunking a new instruction into a new collector, which was the warp 2 instruction, which means by cycle 2, its registers are available to read also. Okay. And so I'm taking a look at what's available to read. And I see that, you know, basically it's got 2 inputs. It's got R2 and R5 in 2 different banks, 1 and 3. And then I also see that's what's going on here. So the 7 that was left over from the first instruction is in another bank 0. So I could actually do all 3 of those in this cycle. Because there's no, basically it's conflict free, right? This is like happiness at this point. Like all of the pending registers get read. Okay. Does anything happen on the execution units yet? No, right? Nobody's actually got all of their inputs yet, so nobody can actually go and issue to the execution. Questions on this so far? Did you have the same answer so far? Okay, so you can do the next cycle. So what happens on cycle 3?
Work 3 R5.
Yep.
Work 3 R2. Then I executed work 1.
And then you executed warp 1. Okay, Zach, do you have the same thing? That's what I also had. Now there is a choice here, right? In theory, both warp 1 and warp 2 are eligible. There's no dependencies between them. You could have done 2 or 1. It's valid. I don't know if I explicitly tried to like take you away from that in like the scheduling mechanism. I
said maximize.
Oh, okay. Did I say something like that to try to? Typically, you know, yeah, I will try to block it so there's only one correct answer. If you had picked warp 2 because you missed that little detail, I would usually not really care, but I try to have the right answers being all the same. It's very easy to mark. So I try to like hurt you in the right direction. But you know, both are eligible unless there's some criteria that says that should have prioritized one over the other in the question itself. Okay, and in this question, I think there was that. So okay, good. Are we good so far? So on this cycle 2, on the cycle 3, these reads happen. I actually start executing good work. And I am also now, like, I'm also filling another collector unit with this other warp zero add, right? So I have these two first instructions that are basically done doing all of their reading. And then I have this other warp instruction from warp 3, which came in and it did both of its reads, right? It did R2 and R5 both in this cycle because there was no bank conflict and everything was open, right? This was kind of like a good kid, like a wide open field. So Zach, what happens in cycle 4?
Bank 1, warp 0, R2. Bank 2, warp 1, R4, right?
Yep. And what is going on in the execution units? Warp 2. Okay. I didn't ask you to actually specify read or write, and the fact that this box is actually a little bit a different color wasn't meant to be that way. It's because I did some paint art on a previous PDF. I left the box there, but it sort of worked out nicely that this ended up being right anyway. So you had to schedule the write, okay, and the writes get priority, right? And that was said, and that should be the case because you want stuff to finish. So the write here was happening because in cycle 3, I finished the work of warp 1. And then I went ahead and did the write on warp 1 register 4, which was in bank 2 based on the mapping. And then I also was able to concurrently schedule a read from warp 0. I scheduled the read to R2, but I could not schedule the read to R5. Why? There's a bank conflict, right? I said there's one read write per register bank. And so if it's being occupied by the write, then you can't use it for the read. And so that means it's going to have that read is going to have to get delayed. Okay. All right. So you got the same answer too. All right. What's the next one? Warp 2 register 1, right? Yep. And then right close. It's all right. You would have got the points for that. And then right back or execute for warp 3. Is that what you said? Yeah. Okay. Zach, do you have the same thing? Yes. So what happens here? Well, this one was pretty easy, right? It was sort of kind of a wide open field. So warp 3 got all of its operands on the last cycle, right? So it read R2 and R5. Those are now in the operand collector, right? And so that means it can go, and it's actually the only one that can go. So it gets the execution unit. And then I execute, and I schedule the write for warp 2 R1 in this cycle. And so then what's pending? What's left over to be pending here? Warp 0. Warp 0, what register? R2, right? Warp 0, R2. Or sorry, I'm sorry. Warp 0, R5. Yeah, bank 2. Warp 0, R5 is still pending. It got screwed, right? It's like, oh, I want to go. Oh, there's a write. Oh, I want to go. There's a write. So it keeps getting delayed, right? There's a continual bank conflict on the write port. And then what happens in the last cycle? Or the last cycle in this diagram? Somebody else, people should be following along at this point. So tell me what happens here on this last cycle. So who wants to volunteer and tell me? Yeah, you're not even in this class. Somebody else. Yeah. Right. Okay, so warp 3 right back, right? So warp 3 is going to go to R1, right? That's because it finished here, so that's essentially going there. And then what's the other one? Right. So finally, warp 0 gets its R. Now the writes have delayed, and then keener students added extra cycles, but I actually only wanted the 6. Right. If I give you a diagram and it ends at a point, that's all you have to do. In the next cycle, of course, now you would have read everything, so you could have actually executed warp 0, and then warp 0 would write back, but everything's kind of open because the pipeline is drained at this point. It's kind of uninteresting. Okay. Questions on this? All right. How do people do on that question? Let's see. That one was question. Yeah, that was like 73%. And I was reasonable about marking this, right? Because these things were you can go wrong on step 2 and then sort of propagate. Like, I looked to see if you knew what was going on. And a lot of people got this 100% right too. So it was fairly well done. And like I said, the absolute worst question was the memory mapping one at like a third of 30%. or something, and the overall average was, yeah, in the seventies. Okay, and that's it, that was the exam. So my intent with this exam is like, you know, not to have gotcha questions necessarily, but I do want to test to see if you understand the material, right? That's sort of what it's meant to do. And there was a bifurcation. Students who didn't understand the material did not do well. There was a minimum, right? Like in a grad class, 33% on an exam. That's 70%. That's not great. And it was actually, this is just the in-person students. The online students skewed actually worse. So I did get a separation from students who were unprepared. If you've solved this exam and you're like, okay, this seems good, then you should be fine. If you're looking at this exam and you're like, oh crap, I don't know that I could get any of these right now, you have a week. You know, and I would expect a sort of a similar level of confidence on the exam I'm gonna give you. And some of the questions will have similar flavors. They may even run similar mechanisms. The point distribution may be, you know, shifted a bit, try to test other things a little bit more. But that's what you can expect. Any questions? Yep.
What is the physical difference for, within a register file and you add banks? Are you just partitioning the same registers and you have literally separate copies? So it's basically extra register files and then you have a specific read and write port for each bank?
So, okay, so what you're describing is replication. If you just replicated the same values in multiple places. Banking is just, so the actual hardware itself is the same, right? It's a bank, it's got ports. The difference is what you store versus in replication versus banking. In replication, you have an exact copy of two things in two places. So that means that all of the registers are in this place, all of the registers are in this register file, and all the registers are also in this one. So now when you write, you have to make sure that they both update at the same
I'm
time.
meaning that as long as all of these banks have separate registers that are completely different from each other, and each bank has its own rewrite ports, that's just what the hardware structure is.
Yeah, a bank generally, if we say that a bank has one read-write port per bank, and there's 4 banks, then your total bank throughput is 4 ports, as long as you don't have bank complex. Right? Does that make sense? And the ideal case, right, from an architecture is just multi-porting a structure where you can access anything on the same cycle, right, and get 4 ports. But that's just really hard to implement at size. Okay, makes sense. But good question. Other questions? Another thing that comes to mind that I might ask you about that's detailed is what's going on in the memory system. I didn't really talk about any like cycle by cycle what happens in the memory system in this exam, right? It was just sort of the core level. The only thing I asked about the memory system was really that sort of address mapping bit. So understanding, what would happen on an L2 miss or something, right? So understanding how the memory system is working, how a memory controller might deal with the memory system.
Kind of like the example that you went through last.
Which one was this?
I don't remember. You went through a couple on different subsystems.
Yeah, I tried to go through some examples. I don't know. Yeah, similar, but potentially different. I can't remember what example I'm particularly thinking of. I haven't written the exam yet, so I don't actually know what's on it, but. Yes. It should be, I think this one was what, 60-40, was it 50-50? It'll be somewhere in that ballpark. So it'll either be 50-50 right on or 60-40 one way, 60-40 the other way. You can expect sort of that range. Okay. Other questions? Yeah.
Are you gonna post these solutions?
Yeah, I'll post them. Even though, so that you didn't have to show up today, I guess, but maybe this was fun for you. I will post these solutions so everyone can see them. All right. That's it. I'm not gonna have class on Thursday. I will still hold my office hours this week. TA, I think also is holding their office hours. But other than that, I will see you. Show up on time. I am gonna be on time. Okay, I'm gonna be 5 minutes early. I know that I have not been the most punctual this semester. I've never been super late, but hey, I will be early and I'll make sure that so we can start on time and give you guys as much time as I possibly can for the exam. Okay? So nothing Thursday. I'll see you all on Tuesday and good luck. Thanks.
May I ask you an off-topic question?
Yeah.
Do you do jujitsu?
I do not do.
Oh, a lot of wrestling.
Oh, really?
Yeah, you said, did you guys see what this like was on?